After understanding the first method or first test of derivative, we now do one example to actually understand how it works. So now I have taken this function fx equal to x cube minus 3x plus 3, and you can see this graph is is there. This is the graph of this function, and there are 2 points. You can say this is x equal to 1 and this is your x equal to minus 1. So these are the 2 points which are actually, you can see, these are the critical points also, because here that slope, if you draw the tangent, then this tangent will be 0, slope of the tangent will be 0, and if you draw a tangent at this point, the slope of the tangent will be 0. So your x1 and x2 are the critical point, but we'll find this critical point with the first derivative. So we'll find f dash x. So f dash x will be 3x square minus 3. Now you can see 3 you can take common, so this is x square minus 1. And now to get critical point, I am writing this here, to get critical point we put f dash x is equal to 0. So you are going to get x square minus 1 equal to 0, which implies that x equal to plus minus 1. So it means there are 2 critical points. Now we have to check which critical point is the will give you the maximum value and which critical point will give you the minimum value. If you draw the function, then this is very understood. This you can see that x equal to minus 1 will give you the maximum value, and this x equal to 1 will give you the minimum value. You can see this way in the somewhere the in the, and this is, you see, this is local maximum, local minima they are asking. Means they are asking about the valleys or the top hills. They are not asking about you. Otherwise, if they don't say what is local maximum, local minima, then there is, this function is going to infinity. It means there is no maximum value of this function. Similarly, this function is going down, so there is no minimum value of this function. But we are not saying to find maximum value and minimum value. We are saying you to find local maximum value and local minimum values. Local maxima and local minima are found around your critical points. So keep in mind this very, very important thing. Now we actually want to see at x equal to, we take first at x equal to 1. So we go in this way, that we take first we take some smaller point, 0.9. We take x as 0.9. Actually we want to see that what happens here, that f dash x, you see, we have to decide the sign of f dash x. This is your f dash x. If you take 0.9, then you can easily say what is going to happen. This is 0.9 means 0.81. This will be 0.81 minus 1. So this is going to be negative. So this is going to be negative. And now f dash x, you take x equal to some bigger point than x equal to 1. So this is 1.1. So if you put x equal to 1.1 here, then this is going to be positive. So now you can see that x equal to 1, the tangent, if you take some smaller point, then tangent slope will be negative, because the tangent will be have angle, this angle will be, for example, if I draw the tangent here, this angle is more than 90 degree, so it's negative. And if I take this point and if I draw the tangent at this point, this angle is less than 90 degree, so it's going to be positive. So you can conclude now that x equal to 1 is the local minima and local minimum value is f1, or you can say f1, you can put the value here in this function 1. This is minus 3, this cancel, this is 1. So your f1 is going to be 1. So this is the way that you decide. Now we take at x equal to minus 1. So now we take some value smaller than x equal to minus 1. So you take some value smaller than, so this is 1.1, you may take minus 1.1, or some value bigger than this, you can take minus 0.9. So now we check here what is the sign of f dash x. You put this value minus 1.1 here, so it's going to be positive, and if you put this value here, then f dash x is going to be negative. So it shows that x equal to minus 1, you can say x equal to minus 1 is the point of local maxima. This is the point of local maxima, and f minus 1 is the maximum value, and you can calculate your f minus 1. So you put the value here, this is 3 minus 3, this is now the maximum value. So we calculate this here, x this is cube minus 1 plus 3x plus 3, so it's going to be 5. And in the graph also you can see that maximum value is 5, so this is going to be 5. Now we'll discuss the second derivative test, which is the most important, because maximum questions will be solved with the help of this second derivative test. If somewhere this test fails, only then we'll use the first derivative test. Otherwise, in all the questions we'll be using second derivative test. Now understand what is that derivative test. Let f be a function defined on an interval I and c belongs to I. Let f be twice differentiable at c, then so the first condition is that the function should be you should be able to differentiate it twice, otherwise second derivative test cannot be applied. So x equal to c is a point of local maxima if f dash c is equal to 0. You remember that c is a critical point. The c here that we are mentioning is a critical point. So x equal to c is a point of local maxima if f dash c is equal to 0 and f double dash c is less than 0. Then the value of fx is local maximum value of c. And on the second hand side, if f dash c greater than 0, means f dash this is f dash c is equal to 0, this we are taking, and after that we are going to discuss two cases. This is your case 1, then f dash c less than 0, and if this is the second case, that f double dash c greater than 0, then fc is called local minimum value of f. And the test fails if f dash c equal to 0 and the function is double derivative is also equal to 0 at that point c, which is a critical point. In this case, we go back to the first derivative test. Now I explain you the importance of this double derivative. You know that critical points you will obtain either at the valley or at the top hill. So try to understand what this mean. This is your fx x square, and if you draw the graph will be like this. If I ask you, then that this function will have critical point is, you can see that 0 is the critical point, right? Because this f dash x will be, if I calculate this f dash x, then it is 2x. Put f dash x is equal to 0, then you are going to get x equal to 0. So it means that x equal to 0 is the critical point. Now why we find the second derivative, that is very important. Now if I draw the second this function 2x, then 2x is a line. If I say this y equal to 2x, this is a line. This is going to give me the slope of the tangent. For example, if I take x equal to 1, then y is going to be 2. If I take x equal to 0, then y is equal to be 0. So this is going to be like this, and if I take some negative values, it's going to be like this. So this is these are the lines which are giving you the tangents, and or you can see how the tangents are behaving. If this tangent is this side, then it is going to be positive, slope of the tangent is going to be positive, and if this is side, then this tangent is going to be, slope of the tangent is going to be negative. So what that second derivative reflects, If I do second derivative, then this is 2. And if I plot, then y equal to 2 is this line. So actually first derivative just tells me where the tangents will be going through. But second derivative tells me whether this function is concave upward or concave downward. If double derivative is positive, it means this is concave up. If this is concave up, this is very much sure that the function is going to have the minimum value. If this concave is up, then this function is going to have the minimum value. So this is clear from this. Now take this example. You can see this function is concave down. This corner is also called cusp. So but this is concave down. If I differentiate this f dash x, if I do again, then I am going to get 2x this, and x will be 0 is a critical point. And if I do double derivative, then this is going to be -2. So this -2 is going down. So whenever second order derivative is going down, it means this function will be concave down. And if it is concave down, you know that function will have the local maximum value. If this function is concave up, then function will have local minimum value. So this is the importance of this second derivative test. Now we'll take one example to actually understand how that method works. So we apply this second order derivative test to find the local maximum, local minima of this function. So first we differentiate it. F dash x is going to be, this is 6x square, this is 12x plus 6. So you take 6 common, then it's going to be x minus 1 whole square. So to get critical point, we will find this, we put f dash x equal to 0, which implies that x is going to be 1. So x equal to 1 is the critical point. This is the only one critical point. It also means that this graph, if you draw this graph, this either it will be, have a valley or top at x equal to 1. And listen again, this function will have either a top of the hill or valley at x equal to 1. That we have to check whether it has a valley or it has a top. Now we differentiate double derivative f double dash x. This is going to be 12x minus 1. So if we put x equal to 1, then now you see double derivative 1, this is going to be 0. It means your second order derivative fails. Now in that situation we have to apply our first derivative test. So it means you will take x equal to 1, so you take some value more 0.9 or you take some value 1.1 and check the f dash x sign. So you see 0.9, if you take, it's going to be positive, and if you take x equal to 1.1, so even in that case it's going to be positive. So you see that at x equal to 1 the function the derivative sign is not changing. So you can say that x equal to 1, I'm using different pen, so x equal to 1 is neither a maxima nor a minima. So this is important to understand that second derivative test works only when this f double dash is not equal to 0 at that critical point. Now we'll take another example. Let's take an example, fx equal to x cube minus 3x. So to find the local maximum, local minima, we have to differentiate it first. We are going to apply the second order derivative test. So this is 3x square minus 3. You can take 3 common, so this is x square minus 1. So put f dash x is equal to 0 to get the critical point. So you are going to get x is equal to plus minus 1. So it means there are two critical points, plus 1 and minus 1. Now we find double derivative f dash x. So this is going to be 3 and this is 2x. So ultimately this is going to be 6x. So now f dash double x derivative is 3x. You put the value x equal to 1. First we put at x equal to 1. So it's going to be 6 into 1. This is 6, which is positive. So if it is positive, it means the function, this is the situation, you know, will be concave up. If it is concave up, that means you are going to get the minimum value. So you can say that x equal to 1 is the minima, local minima, you can say local minima or local minima, and minimum value of this function will be f1. So if you substitute here, then f1 will, this is 1 minus 3, so this is going to be minus 2. And now we check double derivative of this at x equal to minus 1. So if I put x equal to minus 1 and the sign, you can see 6 will be 6 into minus 1, this is going to be minus 6, which is less than 0. It means you see this graph will have the concave down, and down means will have the maximum value. So x equal to minus 1 is the local maxima, and maximum value you can say f1, this minus 1 you put, so this is going to be minus 1 cube minus 3 into minus 1. So this is minus 1, this is plus 3, this is going to be 2. So your maximum value is going to be 2. So this is the working rule how you apply the second order derivative test. We have also discussed if this test fails, then how you have to go.